there's a, so you're asking if a script can be any size. There's a check in the Bitcoin protocol that won't let a script be over 500 bytes. I think it's like, yeah, I think the individual scripts can't be 500 bytes. So like either the script sig or script pub-p, so whether it's in the input or output, it's 500 bytes max. And then one other relevant comment, like, so there is, like, you can't do just anything, right? So you can't have like a 200 megabyte script that does something really sophisticated. You're limited to 500 bytes. Also, there are no loops, and so it's not Turing complete. There's no way to go back and redo something. There's no way to have, like, I don't know, have a recursive function or anything like that. So you're pretty limited as far as what it can do. But you can do more than just send money around. It's somewhat flexible. Okay, so a transaction is basically just a list of inputs and outputs. So there's a version byte, followed by how many inputs, represented as a variable size integer, and then the inputs, and then followed by how many outputs as a variable size integer, followed by the outputs in order, and then a value at the very end called in-lock time, which is specifies when a transaction can become valid. So this is another one, sort of like sequence number. It's sort of an obscure thing that is not normally used. But if you want to, you can make a transaction not valid until a certain block number or until a certain time by setting in-lock time. Yeah?
And does that mean it's only after that time that transaction will be added to a blockchain?
Yeah.
Is that what it...
Yeah, so if you set, so normally in-lock time is 0. But if you set it to like, I don't know what block we're on now, like 250,000 or 300,000 or something like that. What was it? 367?
368.
Wow, way higher than I remember. Okay, God, dude. Every 10 minutes, you rock. So yeah, you'd have to, if you set it to like, 400,000, then it would not be valid until the 400,000th block.
But when does it get added to the blockchain?
Well, you'd have to, so if you tried to broadcast that transaction, everybody would just ignore it. You would just have to wait until the 400,000th block and then broadcast it, then it could be accepted.
So do you broadcast it after that time, or you just broadcast both sets in some transaction pool and gets...
It does not, I'm not sure, but I doubt it sits in a transaction pool somewhere, because that would be, that's the type of thing, like if you run a full node, you wouldn't want to just accumulate those transactions and let them sit in memory forever because somebody could attack the network, right? Somebody could send a bunch of fake transactions that are not valid for, a million years, and now you've got a million transactions in memory that are not going to be valid forever.
So the onus is on you to kind of send it in after that time.
Yeah, it's up to you to send it later. Yeah, there's nothing built into the protocol. You would personally have to retransmit it later. Okay, so that's it. I mean, I've got more stuff here. I'm going to talk about other standard transaction stuff. Are there any major big questions about this? I'm going to give examples of transactions and stuff. It's probably helpful. I'll just continue and show you guys. So this is just like yesterday. I was just like finishing my slides, and I just grabbed this completely random transaction from the blockchain. So this is just what it looks like. If you look down there at the bottom, you can kind of, if you have paid attention, you can kind of make sense of some of it. So if you look at the very first 4 bytes, that is the little Indian number 1, right? I mean, it says 01000000. That's the version byte. And it's little Indian. That's why the very number 1 is very first. You can see like at the very, very end there, the last 4 bytes, that is the in-lock time, which is 0. So it's just set to 0. And then who knows what the other stuff. You have to parse it to figure out the other stuff. But so that's a transaction. And I'm showing, so I'm also showing the ID. So I mentioned this later, but I'll say it more than once. So the hash of a transaction is shown there in the hash. So that's just the SHA-256 hash of a transaction. The reverse of the hash is what's actually displayed. And again, this is another question where you'd ask me, why would you display the reverse of it? I don't really know, other than often hashes are interpreted as numbers in the Bitcoin protocol, but they're interpreted as little Indian numbers. So if it's displayed, he displays them in big Indian. So I don't know. So anyway, the ID is like the reverse of it. So if you compute the hash of a transaction and it comes out wrong, you're like, I did everything right, well consider just reversing it and maybe it's just backwards.
Just a question. Yeah. 2 slides ago, I think you said version is
up and landing the next one.
That might just be wrong. I probably looked that up. I don't off the top of my head remember what it is. That's probably just incorrect. Because this was a real, yeah, it's version byte first, and this was in the yeah, I don't know. I might have mistyped one. I don't know. But good question. I don't know what the version byte is. In other words, don't trust these slides. It might not be 3 because this was a real transaction. It's obviously a version byte of 1. So yeah, I don't know.
Okay. We'll try to get an answer. If you give that to me, we can put it out later. But tell us what that version is indicating again.
Oh, okay, so you could imagine, like, you know, when Satoshi was creating Bitcoin back in 2008, it's like, well, here's a way to build a transaction, but maybe I'm doing something subtly wrong. You know, just like if you build, like, design a network protocol or something like that, where you're like, well, maybe in the future we'll want to do something different. Maybe we want to extend it. So the version byte is there. I don't know how it's parsed. It's either like, you say something like, you know, if the version byte is not this, then it's invalid, or if, you know, or I don't know how the check works, but the idea of it is just that in the future we could update the structure of a transaction and we'd use a different version byte. Okay. All right, so this is, you probably cannot see the details of this, and I'll go through and explain what this is, but this is just, I parsed the transaction using my own transaction parsing code. So this is the same transaction, and we'll zoom in here and look at what an input looks like. So I show, so this is just like I parsed the actual transaction. So this is showing us what the previous transaction's hash is. It's showing us which output it was, because the previous output was quite a big one, so it's the 18th output. And then it shows us what the size of the script is, so that's hex, it's 6A, whatever the hell that is in bytes. And then the script is just a normal script sig. So that's just, the script is pushing something to the stack, and then pushing another thing to the stack. And what it's doing is pushing a signature to the stack, and then pushing the public key to the stack.
So is that the R and the S you were talking about earlier?
It's the signature, contained in the signature, yes, is the R and the S. So if you look at the signature, I can't remember if I show this. Let me quickly check if I... Yeah, okay, I do. So I'll answer that question in greater detail in a second. Okay, so that's the input. Here's just the output, so it shows us the script. So yeah, the output is slightly simpler. There's the value is sending 3.3 million Satoshis. So that's, I think that's like either 0.3 or 0.0. I think it's 0.03. It's 3 million. I think it's 0.03 bitcoins. And then the length of the script, and the script is, this is like a normal script pub key, which is, it always looks like this op dup, which is duplicates op hash 160, and then it pushes the address, and then op equal verify and op checks it. So we'll talk about this in slightly greater detail. So here's, so these are just the scripts. So what I did here is I grabbed the script sig, which we just saw, and then the previous transaction script pub key. Because that's, from the previous transaction is where it's giving you money that you can then spend. So it's the previous script pub key and then the current script sig that are executed. So this is that script sig. So the signature, I guess I don't think I ever parsed the signature, but to answer your earlier question. So the signature has the R and the S values. So if you look at it, it should make sense. Like it starts with the 3-0, which is how a signature should start. If you look at the very end of it, it ends in a 0-1. The 0-1 is that 1 byte hash type, which if it's 0-1, that means sig hash all, which is the normal way. And then in between there are the various header bytes, as well as the R and the S value. And then that's followed by the public key.
Sorry,
so it says, the reason why it's, yeah.
The 71 and the 33, is that the lengths?
Yes, exactly.
Okay.
So the 71 says push 71 bytes to the stack. So the simplest push data opcodes are just a number. So 71 is a valid opcode, which means push 71 bytes. And so all the, if you need to push more data than that, use a larger opcode, like there are opcodes like op push data 2, which says use the next 2 bytes to represent the length. But if it's a small value, like if it's just 71, you can use the 71 opcode, which means push 71 bytes. So that's what that means. And the 33 means push 33 bytes. And, oh, and you can make sense of the public key too. Like it says push 33 bytes, and that starts with a 0-3, which is like the header byte of, it's one of the 2 header bytes for a compressed public key. So this means, it means either the Y value is odd or even, whatever, one of the 2. This was, oh, okay, so I showed, oh wait, I think everything, okay, so that was not, this was actually the correct output. Okay, on the next slide, then I showed, this is the one that has the previous script pub key. So this is the one that, this is sort of the script that actually gets executed. So it executes this script sig and that script pub key. And then one note about all this stuff, which is that the fee in a transaction is just the outputs minus the inputs. So if you're sending 1.0001 bitcoins, or sorry, if you're sending 1 bitcoins, but all the inputs add up to 1.0001, then that means the fee is 1 minus 1.0001, which is 0.00001. So it's outputs minus inputs. There's no fee placed or something, and that's all it is. Okay, so now there are, so we briefly mentioned before how, like, you know, a script has to be at most 500 bytes. Early on in the first couple or so years of Bitcoin's history, there were a bunch of like DOS attacks on the network. So the core developers, which included Satoshi while he was still sort of a member of the community, made several changes to Bitcoin to try to minimize DOS attacks. And sadly, that meant making script less useful. So one of the things they did was they only, like the standard Bitcoin core client now, only relays standard transactions. So if you try to do something non-standard, which you may want to do for totally legitimate reasons, but maybe you want to do something that's some obscure attack on the network that no one has thought of before. There's basically a whitelist of transaction templates that you have to fit. Otherwise, your transactions aren't relayed. Now, you might be able to construct a valid transaction, but the only way you'll get that in a block is if you are a miner or you send it directly to a miner who is willing to mine it. But otherwise, transactions that aren't standard are not relayed. So I'm just going to show like what are the normal standard transaction or script types that will, I'll explain how they make a standard transaction. So this is like the standard thing. You push, so the script sig, the part where you're spending it, is you push your signature, then you push your public key to the stack. So the stack consists of a signature and a public key. Then it executes the script pub key, which does op dupe. So I could have shown graphics of this, but you could like work this out on paper. It duplicates the public key, so now there are 2 public keys. Then it does op hash 160, so it hashes the top thing on the stack. And then it compares that to, or then it pushes the pub key hash, so now there are 2 hashes that ought to be equal, because what you're doing is you're saying I'm pushing my public key, and it certainly better be the public key that corresponds to that address. So you run op equal verify, and then assuming that passes, it pops those things from the stack and then runs op check sig, which now the only things on the stack are the public key and the signature, and it makes sure that the hash of the transaction, you know, and the public key correspond to that signature, right? Yeah.
When you talk about the stack, I know this is a stupid question. I missed the first class. What do you mean?
Okay, okay, great question. So what is a stack? So when you execute a script, the Bitcoin scripting language has just what's called a stack. It consists of a stack of data. So it's literally like a data structure stack where you can push data to it. So it's it's analogous to a stack of paper or something, a stack of books. So you can push a book, and that means you now have 1 book on the stack. And you can push a second book, except it's not books, it's data, and the data can be any number of bytes. So you can push 1 byte to the stack, and now you've got a byte. Then you can push 6 bytes. So now you've got 6 bytes on top and then 1 byte on the bottom. So now if you say something like you've got 6 bytes and 1 byte, and then you say op equal verify, it'll try to see if those 2 sequences are equal, but they're not equal. So if you did op equal verify in that, it would say false. So it's just like, it's a stack of data, and you can push stuff to the stack and you pop stuff from the stack. And there's one other complicating factor, which is that there are actually 2 stacks. There's an alt stack, and so you can do things like push stuff from the stack to the alt stack, or like move it to the alt stack. So there are operations that do that. And then one other final detail, I sort of mentioned this before, but normally in like a computer programming language like in C, you've got a stack and a heap. So if you like allocate memory, what you're doing is you're allocating memory on the heap. And the heap is like, it's not a stack, it's sort of random, right? It's like you're not pushing things on top, it's just somewhere in the heap. And there's nothing like that in Bitcoin. There's only a stack. And for some reason, there's also an alt stack. I don't know why, but that's just how it is. Yeah?
In the second script of pub key, the key hash over there, is it the same as the one before?
Okay, so in this little script here,
Yeah.
so in this, the way this should work is like when you mean is the one that I actually showed before, like this one? Like this here is, so this is the same thing. I'm like, this is like, you know, sort of drawing out what the scripts are. So this hash right there, the value that you see in the script pub key at the bottom,
Yes.
it says 20 and then it shows a bunch of hex values. That is the hash of the public key. So if you were to work this out, assuming I copied and pasted this correctly, if you took the public key and the script sig there and you hashed it, you should get that value. It's the same value. It's the hash of the public key. Yes?
So that
Oh, sorry.
You mentioned the possibility of having a transaction to be executed future block or future time.
Yep.
Would there be a security concern about double spending in that case if it's broadcast too early?
No, there would be no double spending concern because let's suppose you used in-lock time to lock up a transaction. So you say this transaction is not going to be valid until the 400,000th block. And then you tried to, and then you gave that transaction to someone and said, I'm not paying you now, but this is a valid transaction and will be valid at the 400,000th block. And then you screw your friend and you make another transaction that spends the same money to a different address that is valid and does go on the blockchain. Well, they would immediately know because they can just look at the blockchain and see that the output that you had used in that transaction you were trying to give to them has now been spent. So that transaction you had created that's not valid until the 400,000th block is definitely no longer valid. And they can see that by just looking at the blockchain.
But that transaction hasn't been submitted, right? It's still sitting with you. Right?
Yeah, I mean it's you say hasn't been submitted, and it's like yeah, you would not have broadcast that because it would have been pointless. So the one with the in-lock time. But what do you do? Like if you do that, you're probably trying to one use of in-lock time is to prove to someone that you have locked up funds.
What is in-lock time? Maybe I missed the word there.
Okay, in-lock time is just it's the last value in a transaction that says what block your transaction will be valid at. That's the definition of in-lock time.
Okay, right.
Yeah.
Right.
And so you could just put it 0, and it'll go into whatever block is currently being generated.
So normally it's 0. Yep, and it's immediately valid. And so here's an example of a use of this. So a lot of websites have a problem with spam. But they don't necessarily want to charge for money because maybe people don't want to pay money to log into this website. So let's suppose you want to limit user accounts, but you don't want people to pay. What you can do is people can prove that they have locked up funds using in-lock time. So you create a valid transaction spending 1 Bitcoin, whatever, $150 or whatever it is today. And you can sign data that says, I own the private key corresponding to this 1 Bitcoin transaction that will not be valid for, until the 400,000th block. So you can basically prove that you have locked up funds.
But you can also spend it before that, right?
Well, you could spend it, but if you did that, they would know, right? So if you could do something like here's an example. You could if you did it that way, if you locked up money, what the website would do is if you did spend it, then you're logged out or something. You can't use the website or something. That's not a very good example, but there are uses for in-lock time.
But you can only check within your system because it's not transmitted and it's not in the block.
Yeah.
So back to the stack. So once you've got stuff in the stack, what happens to it then?
Okay, so
What's the execution cost?
these are great. I like avoided putting information about the stack in here just because somebody was going to talk about that later, but I'll answer your question anyway. So, because they're good questions. I should have put more because it's so relevant to all this stuff. So here's how it works. When you like validate a transaction, first of all, if you want to validate a transaction, you have to run the scripts. So you look at the inputs of the transaction, and you go through and you say, okay, input number 1 has this script sig in it. Now I need to find the script pub key from the output of the input transaction. So you go retrieve that script pub key. You then take the transaction that you're considering, and you take the script sig, and you take the script pub key, and you put them into the eval script function in Bitcoin Core. And the eval script function will first execute the script sig. And the script sig almost always pushes a signature and pushes a pub key to the stack. And so now the stack consists of a signature and a public key. Now what it does is, okay, that script is valid, is executed, and there's no falsy value on the stack. I think, if I remember correctly, we'll check that. So there are only true values on the stack, which are just these long sequence of bytes. So nothing, like your script is not aborted. Like if you did something like, you could have a script sig that invalidated a transaction if you use like op return. Op return immediately invalidates a transaction. But assuming you haven't done something like that, you've just pushed values to the stack. There are now values on the stack. The stack stays the same. Now the eval script function will evaluate the script pub key. So now you've got a signature and a public key on the stack, and now the script pub key gets executed, which is this stuff here on the bottom. So the stack is still the same, and now it runs op dupe, op hash 160, whatever, puts some more stuff on the stack, checks it, whatever. At the end, after these two things are executed, and assuming like if there's any point during the evaluation of this that something goes wrong, you might invalidate the transaction. If nothing goes wrong and only true values are left on the stack, then it's valid. So if you end with a 0 on the stack, you've invalidated the transaction. But if you end with a 1 on the stack, then it's valid. So that's sort of what happens. Then there's one other complicating factor, which, yeah, I do sort of talk about this. So there's one other complicating factor is if there's not, yeah.
So does the transaction get validated when a node puts it into the transaction pool, or does it get validated by a miner before they put it into the block? Like when does the validation happen? So is it when you submit it?
It happens, I guess it happens twice, because what you'll normally do is if you run a full node, well, I'm not 100% sure about this. It probably gets checked twice, because as soon as you receive it, you're probably going to validate it before you rebroadcast it. I don't know whether that happens or not. I'm not 100% sure that you validate. But in any case, certainly before a miner puts it into a block, the miner will validate it. Because they don't want to put an invalid transaction into a block, because it'll be rejected by the other miners, and that means the money that they've earned from that block will never be useful, because everybody will reject it.
But it also makes sense to just validate it way beforehand so that it doesn't just pollute a lot of the transaction.
Yeah. They probably validate it immediately, and then now it sits in, miners will create a block. So they'll validate the transaction immediately. If